Forwarding. All right. Welcome back to Crafting Interpreters in Rust. Last time we did some stuff related to improving performance of the interpreter. And so we had like a few little benchmark results, and we wrapped that up pretty nicely. So today we're going to talk about, or we're going to read through chapter 10 on implementing functions, and then we're going to try to implement them. So I will get started. So functions. This chapter marks the culmination of a lot of hard work. Do you mind? Thank you. The previous chapters add useful functionality in their own right, but each also supplies a piece of a puzzle. We'll take those pieces, expressions, statements, variables, control flow, and lexical scope, add a couple more, and assemble them all into support for real user-defined functions and function calls. Function calls. You're certainly familiar with C-style function call syntax, but the grammar is more subtle than you may realize. Calls are typically to named functions like average, 1, 2, but the name of the function being called isn't actually part of the call syntax. The thing being called, the callee, can be any expression that evaluates to a function. Well, it does have to be a pretty high precedence expression, but parentheses will take care of that. For example, get callback, execute, yeah. There are two call expressions here. The first pair of parentheses has get callback as its callee, but the second call has the entire get callback expression as its callee. It is the parentheses following an expression that indicate a function call. You can think of a call as sort of like a postfix operator that starts with open paren. This operator has higher precedence than any other operator, even the unary ones. So we slot it into the grammar by having the unary rule bubble up to a new call rule. This rule matches a primary expression followed by 0 or more function calls. If there are no parentheses, this parses a bare primary expression. Otherwise, each call is recognized by a pair of parentheses with an optional list of arguments inside. The argument list parameter is this, or the argument list grammar is this. This rule requires at least one argument expression, followed by 0 or more other expressions, each preceded by a comma. To handle 0 argument calls, the call rule itself considers the entire arguments production to be optional. I admit this seems more grammatically awkward than you'd expect for the incredibly common 0 or more comma separated things pattern. There are some sophisticated meta-syntaxes that handle this better, but in R, BNF, and in many language specs I've seen, it is this cumbersome. All right, so now he's going to talk about how to parse it. We have already done that. Let's see if he says anything interesting. So the code here doesn't quite line up with the grammar rules. I've moved a few things around to make the code cleaner. Let's see. All right, yeah, I'll just skip it. Maximum argument counts. Right now, the loop where we parse arguments has no bound. If you want to call a function and pass 1,000,000 arguments to it, the parser would have no problem with it. Do we want to limit that? Other languages have various approaches. The C standard says a conforming implementation has to support at least 127 arguments to a function, but doesn't say there's any upper limit. The Java specification says a method can accept no more than 255 arguments. Our Java interpreter for locks doesn't really need a limit, but having a maximum number of arguments will simplify our bytecode interpreter in part 3. We want our two interpreters to be compatible with each other, even in weird corner cases like this, so we'll add the same limit to JLocks. All right, I don't think we did that. Note that the code here reports an error if it encounters too many arguments, but it doesn't throw the error. Throwing is how we kick into panic mode, which is what we want if the parser is in a confused state and doesn't know where it is in the grammar anymore. But here the parser is still in a perfectly valid state. It just found one too many arguments. So it reports the error and keeps on keeping on. Interpreting function calls. We don't have any functions we can call, so it seems weird to start implementing calls first, but we'll worry about that when we get there. First, our interpreter needs a new import. As always, interpretation starts with a new visit method for our new call expression node. Right. Here's the visitor. First, we evaluate the expression for the callee. Typically, this expression is just an identifier that looks up the function by its name, but it could be anything. Then we evaluate each of the argument expressions in order and store the resulting values in a list. Once we've got the callee and the arguments ready, all that remains is to perform the call. We do that by casting the callee to a lox callable and then invoking a call method on it. The Java representation of any lox object that can be called like a function will implement this interface. Okay. That includes user-defined functions, naturally, but also class objects, since classes are called to construct new instances. We'll also use it for one more purpose shortly. There isn't too much to this new interface. Okay, so a lox callable just has the function call, which takes a reference to the interpreter and some arguments. We pass in the interpreter in case the class implementing call needs it. We also give it the list of evaluated argument values. The implementer's job is then to return the value that the call expression produces. All right, call type errors. Before we get to implementing lox callable, we need to make the visit method a little more robust. It currently ignores a couple of failure modes that we can't pretend won't occur. First, what happens if the callee isn't actually something you can call? What if you try to do this? Totally not a function, and then call it. Strings aren't callable in lox. The runtime representation of a lox string is a Java string. So when we cast that to lox callable, the JVM will throw a class cast exception. We don't want our interpreter to vomit out some nasty Java trace and die. Instead, we need to check the type ourselves. Okay, so yeah, you use a runtime type check. We still throw an exception, but now we're proving our own we're throwing our own exception type, one that the interpreter knows to catch and report gracefully. Checking arity. The other problem relates to the function's arity. Arity is the fancy term for the number of arguments a function or operation expects. Unary operators have arity 1, binary operators 2, and so on. With functions, the arity is determined by the number of parameters it declares. This function defines 3 parameters, a, b, and c, so its arity is 3, and it expects 3 arguments. So what if you try to call it like this? Different languages take different approaches to this problem. Of course, most statically typed languages check this at compile time and refuse to compile the code if the argument count doesn't match the function's arity. JavaScript discards any extra arguments you pass. If you don't pass enough, it fills in the missing parameters with the magic, sort of like null but not really value undefined. Python is stricter. It raises a runtime error if the argument list is too short or too long. I think the latter is a better approach. Passing the wrong number of arguments is almost always a bug, and it's a mistake I do make in practice. Given that, the sooner the implementation draws my attention to it, the better. So for lox, we'll take Python's approach. Before invoking the callable, we check to see if the argument list's length matches the callable's arity. All right. So yeah, if we pass a different number of arguments from the arity, then throw an error. That requires a new method on the lox callable interface to ask it its arity. We could push the arity checking into the concrete implementation of call, but since we'll have multiple classes implementing locks callable, that would end up with redundant validation spread across a few classes. Hoisting it up into the visit method lets us do it in one place. So, meaning he put this check into the visitor, yeah. Okay. Native functions. We can theoretically call functions, but we have no functions to call yet. Before we get to user-defined functions, now is a good time to introduce a vital but often overlooked facet of language implementations, native functions. These are functions that the interpreter exposes to user code, but that are implemented in the host language, in our case Java, not the language being implemented, locks. Sometimes these are called primitives, external functions, or foreign functions. Since these functions can be called while the user's program is running, they form part of the implementation's runtime. A lot of programming language books gloss over these because they aren't conceptually interesting. They're mostly grunt work. But when it comes to making your language actually good at doing useful stuff, the native functions your implementation provides are key. They provide access to the fundamental services that all programs are defined in terms of. If you don't provide native functions to access the file system, a user is going to have a hell of a time writing a program that reads and displays a file. Many languages also allow users to provide their own native functions. The mechanism for doing so is called a foreign function interface, native extension, native interface, or something along those lines. These are nice because they free the language implementer from providing access to every single capability the underlying platform supports. We won't define an FFI for JLocks, but we will add one native function to give you an idea of what it looks like. Telling time. When we get to part 3 and start working on a much more efficient implementation of locks, we're going to care deeply about performance. Performance work requires measurement, and that in turn means benchmarks. These are programs that measure the time it takes to exercise some corner of the interpreter. We could measure the time it takes to start up the interpreter, run the benchmark, and exit, but that adds a lot of overhead, JVM startup time, OS shenanigans, etc. That stuff does matter, of course, but if you're just trying to validate an optimization to some piece of the interpreter, you don't want that overhead obscuring your results. Yeah, we saw an example of that with loading the executable. A nicer solution is to have the benchmark script itself measure the time elapsed between 2 points in the code. To do that, a locks program needs to be able to tell time. There's no way to do that now. You can't implement a useful clock from scratch without access to the underlying clock on the computer. So we'll add clock, a native function that returns the number of seconds that have passed since some fixed point in time. The difference between two successful invocations tells you how much time elapsed between the two calls. This function is defined in the global scope, so let's ensure the interpreter has access to that. Okay. What does this mean? Oh, I see. Okay, so he's defining this. He's putting a global environment, global scope, so that he can preload it with this function. Yeah. The environment field in the interpreter changes as we enter and exit local scopes. It tracks the current environment. This new globals field holds a fixed reference to the outermost global environment. When we instantiate an interpreter, we stuff the native function in that global scope. All right, so yeah, he's going to define in the global environment clock, which is a callable thing, and it will be implemented using the Java clock. This defines a variable called clock. Its value is a Java anonymous class that implements locks callable. The clock function takes no arguments, so its arity is 0. The implementation of call, That's interesting that this is a method. That's kind of weird. Okay. The implementation of call calls the corresponding Java function and converts the result to a double value in seconds. If we wanted to add other native functions, reading input from the user, working with files, etc., we could add them each as their own anonymous class that implements LOX callable. But for the book, this one is really all we need. Let's get ourselves out of the function defining business and let our users take over. All right, function declarations. We finally get to add a new production to the declaration rule we introduced back when we added variables. All right, this is parsing stuff. Okay. What's this? Oh, I see. That's the name of the grammar rule. Got it.
Oh, this looks like a parser, but we don't really need it. We should have it already.
Yeah, I know. I'm in general skipping the parser parts. I'm just seeing if he says anything interesting. Yeah, so they can't have more than 255 parameters thing. Yeah, okay. We've got some syntax parsed, so usually we're ready to interpret. But first, we need to think about how to represent a LOX function in Java. We need to keep track of the parameters so that we can bind them to argument values when the function is called. And of course, we need to keep the code for the body of the function so that we can execute it. That's basically what this function class is. Could we just use that? Almost, but not quite. We also need a class that implements LOX callable so that we can call it. But we don't want the runtime phase of the interpreter to bleed into the front end's syntax classes, so we don't want statement.function itself to implement that. Instead, we wrap it in a new class. Okay. So that seems like a typo, right? I don't know. Maybe he meant to say like call of the interface. So we have this LOX function class which wraps his statement.function, and when you call it, it does this. Okay. This handful of lines of code is one of the most fundamental, powerful pieces of our interpreter. As we saw in the chapter on statements and state, managing name environments is a core part of a language implementation. Functions are deeply tied to that. Is he going to actually run through the code? Let's read this code. So we make a new scope, passing in, I think, the global scope. So when you call the function, you make a new scope, starting with global scope, not starting with the scope that you're immediately inside, I guess. And then for all of the parameters in the function scope, you define that parameter with the lexeme of the parameter, so like the name of the parameter, with the arguments that were passed into the function call. And then you execute the body. Okay, that makes sense. All right. Parameters are core to functions, especially the fact that a function encapsulates its parameters. No other code outside of the function can see them. This means each function gets its own environment where it stores those variables. Further, this environment must be created dynamically. Each function call gets its own environment. Otherwise, recursion would break. If there are multiple calls to the same function in play at the same time, each needs its own environment, even though they are all calls to the same function. For example, here's a convoluted way to count to 3. So you do your old recursive count. Imagine we pause the interpreter right at the point where it's about to print 1 in the innermost nested call. The outer calls to print 2 and 3 haven't printed their values yet, so there must be environments somewhere in memory that still store the fact that n is bound to 3 in one context, 2 in another, and 1 in the innermost, like this. That's why we create a new environment at each call, not at the function declaration. The call method we saw earlier does that. At the beginning of the call, it creates a new environment. Then it walks the parameter and argument lists in lockstep. For each pair, it creates a new variable with the parameter's name and binds it to the argument value. So for a parameter like this, at the point of the call to add, the interpreter creates something like this. Then call tells the interpreter to execute the body of the function in this new function local environment. Up until now, the current environment was the environment where the function was being called. Now we teleport from there inside the new parameter space we've created for the function. This is all that's required to pass data into the function. By using different environments when we execute the body, calls to the same function with the same code can produce different results. All right. Once the body of the function has finished executing, execute block discards that function local environment and restores the previous one that was active back at the call site. Finally, call returns null, which returns nil to the caller. We'll add return values later. Let's see. Mechanically, the code is pretty simple. Walk a couple of lists, bind some new variables, call a method. But this is where the crystalline code of the function declaration becomes a living, breathing invocation. This is one of my favorite snippets in the entire book. Feel free to take a moment to meditate on it if you're so inclined. Done? Okay. Note when we bind the parameters, we assume the parameter and argument lists have the same length. This is safe because visit call expert checks the arity before calling call. It relies on the function reporting its arity to do that. Yeah. That's most of our object representation. While we're in here, we may as well implement toString. Okay, is that in the snippet up here? No. All right. So toString is deciding to call it to print out like fn and then the name of the function in these angle brackets. All right. Interpreting function declarations. We'll come back and refine locks function soon, but that's enough to get started. Now we can visit a function declaration. All right. This is similar to how we interpret other literal expressions. We take a function syntax node, a compile time representation of the function, and convert it into its runtime representation. Got it. Okay, so this AST node is what he's talking about with the compile time representation, and then this is a thing that you can actually call. Here, that's a locks function that wraps the syntax node. Function declarations are different from the other literal nodes in that the declaration also binds the resulting object to a new variable. So after creating the locks function, we create a new binding in the current environment and store a reference to it there. That's that. With that, we can define and call our own functions all within locks. Let's give it a try. All right, I don't know about you, but that looks like an honest-to-God programming language to me. Let's see. Is 7:27. Wow, reading the chapters always takes a lot shorter than I think it does. I'm probably finished. So return statements. We can get data into functions by passing parameters, but we've got no way to get results back out. If locks were an expression-oriented language like Ruby or Scheme, the body would be an expression whose value is implicitly the function's result. But in locks, the body of a function is a list of statements which don't produce values, so we need dedicated syntax for emitting a result. In other words, return statements. I'm sure you can guess the grammar already. So yeah, return. We've got, let's see, blah, blah, blah. Parsing. Okay, does he say anything? Yeah, he returns an error if it's not formatted right. Returning from calls. Interpreting a return statement is tricky. You can return from anywhere within the body of a function, even deeply nested inside other statements. When the return is executed, the interpreter needs to jump all the way out of whatever context it's currently in and cause the function call to complete, like some kind of jacked up control flow construct. For example, say we're running this program and we're about to execute the return statement. The Java call stack currently looks roughly like this. So we're visiting a return statement inside an if statement, inside a block, inside a while statement, and so on. We need to get from the top of the stack all the way back to call. I don't know about you, but to me that sounds like exceptions. When we execute a return statement, we'll use an exception to unwind the interpreter. Okay, to unwind the interpreter, pass the visit methods of all the containing statements back to the code that began executing the body. Okay, the visit method for our new AST node looks like this. All right, so value equals null. If there is a value in the return statement node, then evaluate it, and then throw an error called a return. If we have a return value, we evaluate it, otherwise we use nil. Then we take that value and wrap it in a custom exception class and throw it. Okay. This class wraps the return value with the accoutrement Java requires for a runtime exception class. The weird super constructor call with those null and false arguments disables some JVM machinery that we don't need. Since we're using our exception class for control flow and not actual error handling, we don't need overhead like stack traces. We want this to unwind all the way to where the function call began, the call method in locks function. Oh, okay, yeah. For the record, I'm not generally a fan of using exceptions for control flow, but inside a heavily recursive tree walk interpreter, it's the way to go. Since our own syntax tree evaluation is so heavily tied to the Java call stack, we're pressed to do some heavyweight call stack manipulation occasionally, and exceptions are a handy tool for that. All right. We want to unwind this all the way to where the function call began, the call method in locks function. All right. So now this is in a try catch. So try to execute it. And if we returned, then catch that and return the return value. We wrap the call to execute block in a try catch block. When it catches a return exception, it pulls out the value and makes that the return value from call. If it never catches one of these exceptions, it means the function reached the end of the body without hitting a return statement. In that case, it implicitly returns nil. Let's try it out. We finally have enough power to support this classic example, a recursive function to calculate Fibonacci numbers. This tiny program exercises almost every language feature we have spent the past several chapters implementing. Expressions, arithmetic, branching, blah, 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 and returns. Local functions and closures. Our functions are pretty full-featured, but there is one hole to patch. In fact, it's a big enough gap that we'll spend most of the next chapter sealing it up, but we can get started here. Locks function's implementation of call creates a new environment where it binds the, this is what I said, where it binds the function's parameters. When I showed you that code, I glossed over one important point. What is the parent of that environment? Right now, it is always globals, the top-level global environment. That way, if an identifier isn't defined inside the function body itself, the interpreter can look outside the function in the global scope to find it. In the Fibonacci example, that's how the interpreter is able to look up the recursive call to fib inside the function's own body. Fib is a global variable. Wait, when did he do that though? When does he put? I'll find it later. Okay. But recall that in locks, function declarations are allowed anywhere a name can be bound. That includes the top level of a lock script, but also the inside of blocks of other functions, or other functions. Lock supports local functions that are defined inside another function or nested inside a block. Consider this classic example. So this is like a closure kind of thing. Here, count uses I, which is declared outside of itself in the containing function makeCounter. MakeCounter returns a reference to the count function, and then its own body finishes executing completely. Meanwhile, the top level code invokes the returned count function. That executes the body of count, which assigns to and reads I, even though the function where I is defined has already exited. If you never encountered a language with nested functions before, this might seem crazy, but users do expect it to work. Alas, if you run it now, you get an undefined variable error in the call to counter when the body of count tries to look up I. That's because the environment chain in effect looks like this. So in global, we have these functions, and then here it just points to global scope, where I isn't. When we call count, we create a new empty environment for the function body. The parent of that is the global environment. We lost the environment for makeCounter, where I is bound. Let's go back in time a bit. Here's what the environment chain looked like right when we declared count inside the body of makeCounter. So I was 0. So at the point where the function is declared, we can see I, but when we return from makeCounter and exit its body, the interpreter discards that environment. Since the interpreter doesn't keep the environment surrounding count around, it's up to the function itself, object itself, to hang on to it. This data structure is called a closure because it closes over and holds on to the surrounding variables where the function is declared. Closures have been around since the early Lisp days, and language hackers have come up with all manner of ways to implement them. For JLocks, we'll do the simplest thing that works. In locks function, we add a field to store an environment. So now the runtime function class has an environment inside it, scope to it. We initialize that in the constructor. When we create a locks function, we capture the current environment. Okay, so this environment is sitting around in the interpreter class, I guess. Yeah, this is interpreter.java, so that's why they have a reference to that. This is the environment that is active when the function is declared, not when it's called. When the function is declared, not when it's called, which is what we want. It represents the lexical scope surrounding the function declaration. Finally, when we call the function, we use that environment as the call's parent instead of going straight to globals. Okay. This creates an environment chain that goes from the function's body out through the environments where the function is declared, all the way out to the global scope. The runtime environment chain matches the textual nesting of the source code like we want. The end result when we call that function looks like this. All right, so this is the invocation of the function. It points to, it's empty, and it points to the environment of the function where it was defined, like the outer function, and then that points to global. Now, as you can see, the interpreter can still find I when it needs to because it's in the middle of the environment chain. Try running that makeCounter example now. It works. Functions let us abstract over, reuse, and compose code. Blocks is much more powerful than the rudimentary arithmetic calculator it used to be. Alas, in our rush to cram closures in, we have let a tiny bit of dynamic scoping leak into the interpreter. In the next chapter, we will explore deeper into lexical scope and close that hole. Let's see, what does that mean? And no design note, so I'll just stop reading there. All right, that is chapter 10. A lot of stuff in there. So let me look back at what he meant by dynamic scoping. It means when you declare a function. No. This is when you are calling a function, right? Hmm. So let's see. So what was this closure thing? Oh, right. So this is inside the constructor, right? No, when you call it. Okay. Right. So now instead of, right, so you pass in the closure. The closure gets assigned when you define this inner function. And then it gets passed in every time you call. Yeah. Okay. Okay. So I don't know how you would make that not dynamic, but we will find out. Anybody have questions or things I should go back to in this chapter?
I didn't quite get on the dynamic scoping, like what's the dynamic part that the I guess I'm not seeing that.
Yeah, kind of me neither, because everything's dynamic, because
Yeah.
this is all being interpreted at runtime. So
And it's not like the code is change the relationship of the functions and the scope with what they're in is changing, right? Like it's yeah, I guess I'm
like
also
this.
just not yeah, like yeah, just trying to
Why don't let's look here and see if we can figure out what he meant. Um, this whole chapter. Okay.
like yeah, I don't see dynamic scope in chapter 11.
Okay. Well, okay, apparently the entire chapter is about that. So,
Oh,
let's see. It's a difference between how the language is supposed to work and how the way we implemented it makes the language work, I think is what he's saying. So a quick refresher, LOX, like most modern languages, uses lexical scoping. This means you can figure out which declaration a variable name refers to just by reading the text of the program. Okay. Here we know that the A being printed is the variable declared on the previous line and not the global one. Running the program doesn't and can't affect this. The scope rules are part of the static semantics of the language, which is why they're called static scope. I haven't spelled out these scope rules, but now is the time for precision. A variable usage refers to the preceding declaration with the same name in the innermost scope that encloses the expression where the variable is used. There's a lot to unpack in that. I say variable usage instead of variable expression to cover both variable expressions and assignments. Likewise with the expression where the variable is used. Preceding means appearing before in the program text, as in not in execution order. Here, the A being printed is the outer one since it appears before the print statement that uses it. Yeah. In most cases in straight line code, the declaration preceding in text will also precede the usage in time, but that's not always true. As we'll see, functions may defer a chunk of code such that its dynamic temporal execution no longer mirrors the static textual ordering. Yeah, like loops. I think you only need a loop to do that. Wait. Okay, we'll see. Innermost is there because of our good friend shadowing. There may be more than one variable with the given name in enclosing scopes, as in, A exists in both outer and inner. Our rule disambiguates this case by saying the innermost scope wins. Since this rule makes no mention of any runtime behavior, it implies that a variable expression always refers to the same declaration through the entire execution of the program. Our interpreter so far mostly implements this rule correctly, but when we added closures, an error snuck in. Defer? What does defer have to do with this? Oh, for the time versus line order thing. Yeah. So if you want to make something execute later in time, but first in text order, then you use defer. Yeah. But when we added closures, an error snuck in. All right. So we define a global. We define A in global scope. We define a closure that prints whatever A is. Ah, I see. So show A is I see. So
it's like whatever's closest or something. It's not in relation to the static rules of the code, or
yeah, so the problem here is the A gets captured when we define this closure, right? So at the point where we define this closure, it's the global A. However, if we use the definition of lexical scope here, then it should be the global A here and then the local A here. But
okay.
in our current implementation, it's going to be the global A both times, right?
Because you've defined it once and it's referencing the global A.
Oh, wait. No, he's saying it should print global twice. Okay. Why does it print local block right now?
Is it because the variable A shadows A and then the show A is using the one that's most recently defined?
Yeah, but why? Okay, which environment actually gets used when you call the closure? I guess what we're doing, it's because we're not making a copy, we're doing it by reference. So the one that we're putting into here is literally the same scope as the one in this block. Instead of a clone of whatever the scope was when we defined the function. I think that's what he's going to talk about. I'm not sure though. That's just my guess. Okay. By our rule that a variable expression always resolves to the same variable, right. So this is not literally the same variable as that. It's just the same name.
Right.
That implies the second call to show A should print the same thing. Alas, it prints global and then block. Let me stress that this program never reassigns any variable and contains only a single print statement. Yet somehow that print statement is for a never assigned variable prints two different values at different points in time. We definitely broke something somewhere. Okay. Let me think through why it should be global both times again. So it's because when you define this, according to lexical scope, A refers to this A.
And it shouldn't change.
It shouldn't change. Yeah. So let me think. So is it, let's see, is he going to fix, if you do the thing that I said of like copying the scope whenever it's defined, making like a little copy of whatever scope is in this block when the closure is defined, does that fix it? Or can you think of an edge case?
I would think that would, because you're taking a snapshot of the environment when it's defined.
I wonder how it should behave if the global variable updates, and how can we implement that, because we cannot simply take a snapshot.
So like, yeah. why wouldn't that be what we expect though? So if it's like, okay, hold on. Actually get a text editor. So if it is, that, then if we take a snapshot when we define this, then it will be this value. And then I don't know, like, and then it's irrelevant to think about like, yeah, and then yeah, you do this right in between the calls. Like, it's like instead of doing that, you do this. There's another sort of by value or by reference thing. Yeah.
But would that one change it? Because you're not, the other case, you're declaring a new variable, right? That happened to have the same name.
Yeah. I think that it should print differently. So it should print this and then that. Because the A in here is referring to this variable, and this variable is getting modified. But let me go try that in like JavaScript or something. Translate it. Okay. Let me just try it again. Yep, that's what we said. Yeah. So the A inside here refers to this A. And I don't know if Java does or JavaScript does shadowing, but because it refers to this A, it reflects changes in that A. Yeah. So actually, let me see if it does shadowing. It looks like it does do shadowing, like you said. So yeah, I think we want the exact same behavior as this. Yeah. Okay. Before you type this in and run it, decide what you think it should print. Okay, we read this, my bad. Let me stress that this program never reassigns any variable, We definitely broke something. Okay. I'm not gonna get into this whole chapter. I just wanted to answer the question. So any other questions about the stuff we just read in chapter 10?
Do we already have a call, the equivalent of the dot call?
No, I think we'll need to do a trait or something.
I'm not sure if we need to trade. What we'll need is a representation for external Rust function. That would be a function pointer. And we need representation for logs function. That would basically be like a list of statements.
So yeah, representation. So, but the commonality is like his interface is called logs callable. So both the Rust functions and
It's
the
Java.
Yeah.
We're not using Java, we're using Rust.
Right. I'm saying do we want to at least abide by the same interface for both? Or do we just like make a special exception for the foreign functions?
I think we make something that makes sense in Rust.
Yeah.
And if it
Yeah.
breaks, at least we'll have some.
Yeah. Okay. Let's see. Anything else? What was your question, Paul? I kind of forgot. The
other one was just about the .call, but yeah, the first one was answering.
yeah.
Yeah, so
Okay. Yeah, I think I mean we need to do this, and then we need to also allow executing a Rust function. But like, yeah, he only has one example of this of a native function, so I don't know. Like, and the only reason for having this interface is so that both of those things can be used the same way. So yeah, I'm sure we'll find a good way to do it. Oh yeah, and he has a toString that says native FN. Yeah. Which is weird because it should say like FN clock or native FN clock. Whatever. Okay, so cool. All right. Well, I'll end there. And we'll start implementing this stuff next time. It's a very interesting chapter.